Okay, so this is a video on how to extract metals from their ores. And this video follows on from the video I made on displacement reactions. And when considering methods of extracting metals from their ores, we have to look at their position in the reactivity series relative to carbon. And if you have a look at your reactivity series and have a look where iron is, carbon is, and aluminium, you'll see that aluminium is the most reactive, carbon is the next most reactive, and iron is the least reactive of the three. Therefore, if you've got a compound of iron, for example iron oxide, and you react it with carbon, you can actually have a displacement reaction. The carbon, because it is more reactive than the iron, can displace the iron from the compound, and therefore it kicks the iron out, and you therefore have iron metal. Now, over centuries we've refined this process, and during the 19th century we came up with this process here, which features on probably every 2 out of 3 GCSE papers. This is what's called the blast furnace. And this was developed in Shropshire, near a town called Ironbridge, which is now called Ironbridge. I don't think it was called Ironbridge at the time. And it was developed by a gentleman called Abraham Darby. And what he did was he refined this ancient extraction of iron using carbon, and instead of using carbon, he actually used carbon monoxide in the reaction. And he did it a little bit like this. So in the blast furnace, you need to know that you have 3 raw materials going in at the top. You have iron ore, coke, and limestone. Those are your 3 raw materials that you put in. Now, coke is effectively refined carbon. Iron ore, otherwise known as hematite, is iron oxide, and limestone, which is the raw material, contains a compound called calcium carbonate. And all those 3 things are essential in producing the pure iron at the end of the process. So you can see here, down at the bottom, we have an outlet for iron, a molten iron sitting down at the bottom. So, in at the top goes our iron ore, coke, and limestone. And what happens inside the process, or inside the furnace, this furnace which is incredibly hot, the carbon in there reacts with oxygen, and this produces carbon dioxide. That is a very, very, very exothermic reaction. In other words, it gives out a huge amount of heat. It gives out so much heat that the carbon dioxide is able to react with some more carbon to make carbon monoxide. We balance that with a 2. Now, that reaction only happens in very, very hot conditions, because in actual fact it's endothermic. And the carbon monoxide reacts incredibly well with the iron oxide. Here's my iron oxide from the iron ore, and it reacts with the carbon monoxide to produce iron, and the carbon monoxide takes the oxygen to form carbon dioxide. And we would balance that by putting a 3 here, a 3 here. Let's just count. Our carbons are balanced, our oxygens are balanced, and that leaves us with 2 irons. So that produces pure iron. Now, in this process, the iron is going from having a 3+ charge in the compound. If you have a look, Fe2O3, iron would have a valency of 3. So iron is going from 3+. Over here, it doesn't have a charge, it's neutral. So the iron has in fact gained 3 electrons to go from 3+ to neutral. We've added 3 electrons to it. And the process of gaining electrons, if we remember oil rig, that is reduction. Now, obviously if reduction's going on and we're having electrons supplied, something else has to be oxidized. And here the carbon is oxidized. Okay, it goes from carbon monoxide to carbon dioxide. Now the iron is being reduced, and we would then refer to the carbon monoxide as the reducing agent, because that is causing the iron to be reduced. So we're producing lovely pure molten iron at the bottom, which can be piped out of the furnace, and it flows out, and when it cools it solidifies, and then we can use it for all kinds of things. Okay, iron is very strong. This process is actually cheap, so it's a very, very useful metal. Now unfortunately, in our iron ore, we don't just have iron oxide. We have also some sandy impurities. Now these sandy impurities contain a chemical called silicon dioxide. And it's important this sand doesn't get mixed up in the iron, because if the sand got mixed up in the iron becomes less strong. So we need to get the sand out of the iron just in case it gets mixed up. And this is where the limestone comes in. The temperature in the furnace is so hot that the calcium carbonate thermally decomposes. It forms calcium oxide and carbon dioxide. I'm just going to put a little line here because this is the production of iron up here. Down here, this is the removal of impurities. So the calcium carbonate thermally decomposes to form calcium oxide and carbon dioxide. Now the calcium carbonate which forms then reacts with silicon dioxide, and a compound called calcium silicate is formed, CaSiO3, which is how I remember it. Now the reason for this reaction occurring is you've got two oxides combining. Calcium oxide is a metal oxide, and you should hopefully remember that a metal oxide is basic. In other words, it's opposite to an acid. Silicon dioxide is a non-metal oxide, and hopefully you remember that silicon dioxide sorry for the pause, I just had a big cough. Hopefully you remember that silicon dioxide, being a non-metal oxide, will be acidic. Carbon dioxide is acidic, so silicon dioxide, another non-metal oxide, is acidic. And you'll see that an acid reacts with a base, and this is therefore a neutralization reaction. And this is very, very frequently asked by examiners on the IGCSE specification. They like asking why this reaction occurs, and it occurs because it's a neutralization. Now here we have our calcium silicate. But chemists, we don't always call things by their chemical name, and the nickname that CaSiO3, calcium silicate, has in chemistry is slag. Okay, it's commonly referred to as slag. Okay, and what happens is the slag floats on top of the iron. It's much less dense than the molten iron, so it sits on top of the iron. And the slag is actually quite useful in this form. We can scrape it off the side, we can let it flow out, and we can actually use it to make the foundations for roads. So we do put it to good use. So the carbon, or the coke, and the iron ore is used to obtain pure iron, and the calcium carbonate is used in the process to remove impurities, in particular sandy impurities, silicon dioxide. Now the blast furnace is very frequently talked about on exams. The other metal extraction which is often referred to, and I'm not quite sure why I've got two slides there, but the other metal extraction which is frequently referred to is the extraction of aluminium. Now aluminium can't be displaced from aluminium oxide by carbon. Obviously now I'm hoping that you're asking yourself why that is the case. Remember back to our reactivity series, if we had aluminium oxide and carbon, they can't react. And they can't react together because carbon is less reactive than the aluminium, so the carbon cannot displace the aluminium. So, how do we do it? Well, unfortunately, it's a very, very expensive process, and we have to use electrolysis. So, into our electrolysis cell, we have a mixture of aluminium oxide from its ore, which is otherwise called bauxite, and another substance called cryolite. Now, this all occurs at incredibly high temperature. It occurs at about 2000 degrees Celsius. That is incredibly hot. And it needs to be at this temperature because otherwise the cryolite won't be molten. It won't be liquid. And it needs to be liquid, and the aluminium oxide needs to be liquid, so the ions can flow through the cell. Now you might be thinking, well, why not just use pure aluminium oxide and heat up the aluminium oxide to such a temperature that it melts? And the reason we can't do that is because aluminium oxide doesn't melt until round about 3000 degrees Celsius. Okay, much higher. But cryolite is molten at about 2000 degrees C, and aluminium oxide will dissolve in the cryolite at this temperature. So we put the aluminium oxide in there, the lattice breaks up, so the aluminium ions are now able to move, and the oxide ions are now able to move. So the reason we need cryolite is to dissolve the aluminium oxide at a lower temperature than it would be if it was molten. You might be thinking, well, if it's just to dissolve it, why not use water? And the reason we don't use water for this is that aluminium oxide does not dissolve in water. So, what happens here? Well, if you see, we've got our reaction mixture in the cell here. We've got carbon anodes which stick into the cell. Okay, so those are our positive electrodes. And then we've got a cathode which lines the bottom of the cell. And the cathode is negative. I hope you remember that. So, what happens at the cathode? Well, which species do you think are going to be attracted to the cathode? In your reaction mixture, you have Al3+, and you also have O2-. And it's given away a little bit in the diagram that you form liquid oxygen here, not liquid oxygen, liquid aluminium here. So the aluminium 3+ ions, which are floating around in here, are attracted to the negative charge. And when they hit that negative cathode, they attract electrons off it. And it's the electrons that make the cathode negative in the first place. And you therefore form aluminium metal. And the aluminium builds up and builds up and builds up at the bottom of the cell, and eventually we can tap it off. Eventually it will flow out whenever we want it. Now, if the positive ions go to the negative cathode, the negative ions in here will be attracted to the positive anodes, and that's exactly what happens. The oxide ions in here, O2-, are attracted to the positive electrode. So here's O 2 minus. And oxygen ions relinquish their 2 electrons to the anode. So they give out 2 electrons, and you make an oxygen atom. Now those of you who are thinking particularly carefully about this might be thinking, well, hang on a minute, I don't often see oxygen atoms forming in chemistry. Normally we talk about oxygen molecules. Fair point. Initially the oxygen atoms form, but next to it another oxygen atom will form and the two will bond together. So you in actual fact do form an oxygen molecule. So if that's going to be the case, we need 2 of those, and as each one gives out 2 electrons, that means we have 4 electrons being relinquished overall. And therefore we have lots of bubbles of oxygen coming off around that cathode. Now you must also remember that at 2000 degrees Celsius this is very, very hot. We've got carbon anodes, so effectively charcoal anodes, and lots of oxygen around it at a very high temperature. What then happens is the carbon anodes unfortunately react with the oxygen that's produced to produce lots and lots and lots of CO2. And in the grand scheme of things, that's not really a problem. Okay, yeah, we're producing carbon dioxide, which is a greenhouse gas, but relatively speaking compared to other industries, that's not a huge amount. The problem is because the carbon anodes start to wear away, because the carbon that was on the anode is now being turned into a gas. So the anodes have to be replaced regularly. That's not too bad. The anodes are pretty cheap, but it still is an extra expense for this. Now here, when the aluminium is going from Al3+ to Al, it's gaining 3 electrons. Now you should be asking yourself, is that an oxidation or is it a reduction? And as it's a gain of electrons, oil rig is gaining, so it must be reduction. This second process is an oxidation. It's losing electrons. Electrons are being kicked out. So that's going to be an oxidation. And because both processes are occurring at the same time, we call it a redox. So that's how you extract aluminium out of its ore. It's an expensive process, and there are 2 big reasons why it's expensive. The first big reason is that a lot of electricity is required. And electricity is expensive. So we usually build aluminium extraction plants near power stations. The second reason it's so expensive is that, well, look at the temperature that we have to maintain. So the second reason is very high temperatures needed. So a lot of fuel is consumed trying to keep the temperature at 2000 degrees C. Another favoured question from examiners is, why is cryolite needed in this process? And the reason cryolite is needed in this process, let's choose a different colour, let's have some green, I covered about 3 or 4 minutes ago. The cryolite is needed because it enables the aluminium oxide to dissolve at a temperature lower than its melting point. And maybe you should be thinking, well, why do I need it to dissolve? And it needs to dissolve because the aluminium oxide can therefore conduct electricity. Therefore, the Al2O3 electrolyte can conduct. Now, these two extractions of metals, the extraction of iron and the extraction of aluminium, are very, very popular with examiners. You also need to consider the uses of aluminium. Now, aluminium, despite its high reactivity, is very, very useful because on the surface of the aluminium you get a layer of aluminium oxide forming, and aluminium oxide is very unreactive, and that protects the rest of the aluminium. Therefore, aluminium is used to make food containers. It would be a shame if your food started reacting with the food container. So aluminium is perfect because of that layer of aluminium oxide. It also has a very low density, and this combined with its seemingly unreactive nature due to that oxide layer means it's perfect for using to build aeroplanes out of, because roughly speaking it's quite a lightweight material. Never really say lightweight in the exam, always say that aluminium has a low density. And that's the end of this video on extraction of metals.